Listen a little closer, my friend out there. Something vast is breathing. Beyond city roofs and restless thoughts, the night carries quiet clouds of starlight, nebulae, where new suns begin and old ones turn gently back to dust. Don't rush to see them. Let the room soften first. Feel your shoulders ease, your breath find a slower tide. We'll drift there together, unhurried through dark veils and faint colors, where hydrogen hums and time takes its patient shape. We'll visit the pillars that cradle young stars and the ghostly shells where light lingers after endings. If this gentle wandering brings you comfort, a soft like and a quiet subscribe. Help others find this calm place too, only when it feels right. For now, let your thoughts grow lighter and float like dust in a beam. The clouds of creation are waiting. We'll begin together, warm and slow. Have you ever paused on a quiet night and wondered what truly lives inside those faint, glowing veils between the stars? The dark between constellations isn't empty at all. It holds a slow ocean of gas and dust, drifting so gently that a lifetime is only a small sigh to it. That ocean is the raw material of everything bright. The stars that warm planets, the worlds that grow mountains and oceans, the breath moving softly in your chest. Astronomers call these regions nebulae, from the old word for cloud, though they are not clouds like the ones that wander over your town at dusk. They spread for light years, too thin to touch, and yet luminous in colors set by chemistry and starlight. Some shine with their own glow, bathed in fierce ultraviolet light from newborn suns. Others do not shine at all, but borrow the glow of neighbors and scatter it into a silver-blue mist. And some are darker than any midnight, silhouettes that hide more light than they reveal, as if the sky has placed a hand over its mouth to keep a secret. Together, they are the quiet architecture of our galaxy, an invisible ecology where creation and decay share the same breath. A nebula begins in the deep cold, where atoms wander like snowflakes that never land. Hydrogen first, helium second, with a trace of heavier elements made long ago in older stars. Gravity is patient. It gathers these wanderers into faint threads. With time, the threads thicken, not with hurry, but with steady pressure, like hands pressing a page into a book. In the knots where filaments cross, temperature slowly rises, pressure follows. Inside those delicate knotted cocoons, something extraordinary can happen. Nuclei begin to fuse, and a star takes its first light. The cradle is quiet, but the beginning isn't small. It is the moment a seed decides to be a tree. Yet nebulae are more than nurseries. They are also memorials. Stars like our sun do not end with a single extinguishing breath. After their long, steady work, they loosen their outer layers and let them drift outward, a luminous shell expanding for thousands of years. The exposed core, hot and bright, shines through the shed gas and lights it up like lanterns in fog. In other corners of the galaxy, endings are sudden. Massive stars collapse and then explode, throwing their outer layers into space at thousands of kilometers per second, shredding themselves into filaments and lace. The debris carries gifts: oxygen for oceans, carbon for life's scaffolding, iron for blood and stone, and the quiet dust that will one day collect into planets and perhaps someone's future evening. The galaxy lives by this rhythm: birth, death, renewal again and again, as if the Milky Way inhales and exhales on timescales too long for any one lifetime to feel. From afar, a nebula can look like a smudge, a pale brushstroke across black paper. Move closer with a good telescope, and the smudge becomes a cathedral of gas, dust, and light, a structure stretching across trillions of kilometers. Some are flamboyant, bright as embers. Some are cold and shy. Some are the soft afterglow of a star's final words. At heart, a nebula is simply gas and dust in space, but simplicity doesn't mean sameness. They fall into families with their own moods. There are the emission nebulae, the showpieces. Here, the gas itself shines. Young, hot stars pour out ultraviolet light and strip electrons from hydrogen in the surrounding cloud. In that thin, energized sea, stray electrons eventually fall back into orbit around protons. Each reunion releases a precise color. The most famous of those colors is the deep ruby called hydrogen alpha, glowing at a wavelength of about 656 nanometers. That is the blush you see braided through the Orion Nebula, visible even to patient eyes in a dark winter sky, and in the Lagoon Nebula that swims in summer's Milky Way. The light can feel like a soft flame, but the physics underneath is crisp, an atom calmed after being shaken, exhaling the color of its relief. Another family is quieter, reflection nebulae. These do not make their own light. They borrow and scatter, find dust grains inside the cloud, catch starlight and throw it to us, favoring shorter wavelengths. Just as Earth's sky is blue because air scatters blue light more efficiently, these clouds often appear silvery or azure. Around the Pleiades, a cluster many people learn as children by tracing a little dipper within the big one. Soft, blue veils drift like breath on glass. Reflection nebulae are easy to overlook near brighter companions, but once your eyes settle, they feel like a whisper answered. Then there are the dark nebulae, the galaxy's silhouettes. They do not glow or reflect, they block. These are the densest, dustiest folds of the interstellar medium, thick enough to hide fields of stars behind them. The Horsehead Nebula is one of these, a shape cut from a red glowing backdrop like a shadow against firelight. Inside such lightless rooms, where starlight arrives only as a rumor, gravity works in secret, drawing matter together until new seeds of stars are ready. What looks like absence is often preparation. Not every nebula celebrates a beginning. Some are the final garments of stars like our Sunday. Astronomers call them planetary nebulae, a name fooled into history by early telescopes. In the late 1700s, small instruments showed these shells as round, faint disks that reminded observers of distant planets, so the term stuck, even though planets have nothing to do with their making. What you're seeing is the afterglow of stellar wind and shed layers, lit by the hot, exposed core. The sight is gentle, but the story is strong. A star, finished with one kind of life and beginning another as a white dwarf, while the gas it let go will help build future worlds. Beyond those soft, rounded shells, drama returns. Supernova remnants are the lacework left by an ending so powerful it remakes its surroundings. When a massive star spends its nuclear fuel, gravity wins. The core collapses. A shock wave roars outward. The outer layers are hurled into space at thousands of kilometers per second, and the expanding debris carves filaments and ripples that can span dozens of light years. The Crab Nebula is one famous remnant, the ghost of a supernova that brightened Earth's sky in AD 1054, recorded by observers who watched a guest star shine in daylight. In the Crab's tangle, Particles race and fields twist, and the elements that will someday sit inside bone or bloom in a rocky planet's crust are flung wide. The image of a nebula can look thick and smoky, like fog you could scoop with your hands. The truth is stranger. If you could bottle a teaspoon of nebular material, you would be holding almost nothing emptier than the best vacuum we can make in a laboratory. In many places, a cubic centimeter, about a sugar cube size, holds only a few hundred atoms. On Earth, we would call that no air at all. Yet give that gentle thinness enough room dozens or hundreds of light years, and it becomes a tapestry. Scale changes everything. What seems like perfume turns into weather when it is spread across a galaxy. Most of the mass is hydrogen, the universe's simplest and most faithful element. Helium follows. Trace amounts of oxygen, carbon, nitrogen, and other heavier elements made in stars and scattered by winds and explosions season the mix. Then there is dust, tiny solid grains, often silicates and carbon compounds, only a small fraction of the total mass, but essential. Dust absorbs and scatters starlight, cooling gas clouds enough for gravity to tighten its grip. It also offers surfaces where molecules can form, the first steps down the long path toward complex chemistry. Without dust, there would be no planets, no rich atmospheres, few places for water to hide and wait. A single nebula tells many stories, depending on how you listen. In visible light, hydrogen's glow dominates, sketching where young stars are at work. In infrared, dust becomes more transparent, and the warm cocoons of hidden newborns show their outlines. In radio wavelengths, astronomers trace the cold molecular gas, especially hydrogen, bound into molecules and companions like carbon monoxide that marks the next star nurseries. Each window is a different layer of paint. Together, they make a portrait that a single color cannot. It helps to imagine this process like watercolor, spread across a vast, invisible paper. The pigment is gas and dust. The water is light. Strokes can be sharp, where shock waves from hot stars or past explosions carve edges. They can soften where radiation and time let color bleed. Gravity pulls lines into curves. Stellar winds lift veils and open cavities. A cluster of young suns pushes on its cradle until holes become windows and windows become walls. The artwork is never finished. A shape that looks eternal is only a phase in a very long conversation between pressure, temperature, and time. When astronomers speak of color in nebulae, they are hearing instruments play. Hydrogen sings in red. Oxygen, when doubly ionized, astronomers write it as O3, glows in greenish light, around 500 nanometers. Sulfur, often written S2, tends toward deep orange. In Earth's thick air, or inside a laboratory, these delicate, forbidden lines almost never appear. Atoms bump into each other too often to hold their excited states long enough to release such light. In the spacious quiet of a nebula, collisions are rare, so the atoms can linger, then relax by shining in these rare colors. Through a spectrograph, a nebula becomes a barcode, bright lines and dark gaps that tell you what elements live there, how warm they are, and how the gas moves. It is less a photograph than a melody, each spike a note. Modern telescopes use filters to isolate these notes. A narrow window around hydrogen alpha brings forward the places where new stars are energizing the gas. Filters centered on O3 or S2 reveal the imprint of shock fronts, cavities, and the subtle architecture of flow. Combine them and you get the vivid mosaics that fill books and posters. Reds where hydrogen blushes, greens where oxygen hums, blues where dust reflects, or ultraviolet slips through. Often the colors you see are assigned, translated from invisible light into something our eyes can taste, but they are not arbitrary decoration. They are coded maps of physics. A swirl of green can betray oxygen energized by nearby stars. A river of red can trace dense hydrogen. Faint blue can mark starlight, scattered by dust, or regions where the cloud thins. What looks like art is measurement dressed in beauty. Not all the work in these clouds belongs to light and chemistry. Motion plays its part. Stellar winds from hot stars, streams of particles moving at hundreds or thousands of kilometers per second hollow out bubbles and press on nearby gas, sculpting pillars and ridges. Radiation pushes dust like a breeze pushes pollen. Gravity tightens some regions into knots while letting other parts loosen into drapery. Over millions of years, these gentle pushes and pulls change the face of a nebula entirely. A ridge thins into a filament. A cavity opens into a window. A nursery star cluster breaks free of its cradle, leaving behind a ragged shell and a story. Even the most radiant nebulae live by balance. When the hot stars that fed their glow grow older and quieter, the light fades. Dust can thicken and block what shines. Gas can cool and settle. The cloud relaxes back into darkness, waiting for the next act. Somewhere else, a cluster forms, and the cycle brightens again. In the galaxy's slow rhythm, illumination is temporary, but the possibility of illumination is constant. It is humbling to follow the life of a single photon in this world. A particle of light leaves the surface of a newborn star, invisible to eyes but strong enough to change what it touches. It travels years, then centuries, across a cloud. Maybe it meets a hydrogen atom and shakes its electron loose. Later, when that electron falls home, the atom releases another photon in the red of hydrogen alpha, or perhaps the first photon rattles a dust grain, and the grain sends pale blue outward. Much later, so much later, that entire stories have finished and begun again. That light arrives at a telescope mirror or at the camera of a spacecraft, and then, finally, it spills into an image you can hold in your hands. Your eyes gather it. Your mind leans closer. In that moment, you are witnessing not a painting, but a chain of small interactions gracefully added together across impossible distances. There is a temptation to think of these clouds as separate wonders, each a museum exhibit hung in the hall of the sky. The truth is gentler and more intimate. They are the Milky Way's pulse. Gas that was once inside a star becomes a nebula. A nebula becomes a cradle. A cradle becomes new stars and worlds. Those worlds breathe and write and wonder. And one night a person looks up and feels quieted by a patch of faint color in Orion's sword. The circle closes softly. The elements in your blood and bones, oxygen, carbon, iron, did not come from nowhere. They were made in furnaces and scattered by winds and blasts, cooled and hidden in dust, warmed and lit again, and then folded into a planet that eventually learned to listen. Remember the thinness. A sugar cube of that gas might hold only a few hundred atoms, and yet it can make tapestries 100 light years wide. Remember the numbers that light prefers. About 656 nanometers for hydrogen's deep red, near 500 nanometers for oxygen's cool glow. Remember the names, not as labels, but as familiar rooms. The Orion Nebula, buzzing with young stars. The Lagoon, restless and red. The Horsehead, a shadow cut like a paper silhouette. The Crab, a lace of aftermath from the supernova of 1054. Each is a mood of the same process matter, responding to light and gravity over time's long reach. Every glowing nebula is a conversation between light and matter, a patient dialogue spoken in colors. A photon leaves a star, meets an atom or a dust grain, and the meeting turns into a visible whisper. Millions of such whispers together become a veil, a pillar, a filament, a bloom. Through those layers, we watch the galaxy do its work. Recombination after ionization, scattering after illumination, cooling after heat, collapse after calm. What looks like stillness is movement scaled beyond our clocks. What looks like emptiness is a reservoir of possibilities. So when an image of a nebula finds you reds braided with blue, a hint of green caught in the fold, remember what the colors mean. They are not decoration. They are evidence. They are physics turned tender enough to see. Hydrogen telling you where stars have stirred it. Oxygen humming where energy has passed. Sulfur tracing edges where shocks have traveled. Even the faintest border of brightness is a footprint. It says, quietly, that a star once reached out this far, and the cloud answered. The space between stars holds more than darkness. It holds ingredients and instructions, the memory of endings, the patience of beginnings. In that hush, atoms find their places again. Dust turns light aside, and gravity writes slow sentences only time can read. From such simple exchanges rise the night's most breathtaking sights. Somewhere inside that larger rhythm, the same elements are part of you. These clouds aren't only distant, drifting between constellations. They are kin, their stories braided into your breath, their colors echoed in the warmth of your blood. The universe has been composing itself in these mists for billions of years, painting with light across a canvas as wide as space. Listen closely, and the painting isn't silent. It's a patient conversation. Follow one thread of that conversation, and it leads to dust. In the wide quiet of space, dust often waits at the edge of attention background scenery, soft and overlooked. Yet without it, the cosmos would lose depth and texture. Dust gives starlight something to lean on, drawing shape where there would otherwise be only brightness and black. Some clouds glow because dust helps light linger. Others melt into velvet shadow because dust keeps the light for itself. From this fine substance, planets gather, rings hang in glittering arcs, and galaxies find their contrast and mood. It isn't the dust you sweep from a shelf. These grains are microscopic travelers, sturdy bits of silicate like olivine and pyroxene, flecks of carbon, specks of metallic iron, and tiny beads wrapped in ices of water, methane, and ammonia, each smaller than a wavelength of visible light, closer to smoke than sand. Small as they are, they're reliable companions to chemistry, giving atoms surfaces where meetings can happen and bonds can hold. Their story begins in the old age of stars. When a red giant swells and cools, it loosens its outer layers and breathes them into space, sending out carbon and silicon as if scattering seeds. Supernovae do the same with far more urgency, flinging their contents at thousands of kilometers per second. The debris mixes into the interstellar medium, where atoms condense along the surfaces of these first grains, like frost along a window. Spread thin beyond imagination, this mineral fog is still powerful enough, over distances measured in light years, to alter the look of a galaxy. Light doesn't pass through such regions unchanged. Some of it is absorbed and turned gently into warmth. Some is scattered aside. Some is shifted in color. The effect is like sunlight through wood smoke. The short, blue wavelengths get knocked around more easily, while redder light slips through. Stars seen through dusty lanes appear dimmer and redder than they truly are, a soft disguise astronomers call interstellar reddening. The stars themselves haven't changed. The journey of their light has. From a dark countryside, the Milky Way shows bright bands crossed by inky rifts. To the unassisted eye, they can look like absence holes where no stars live, but a closer look shows layered shadow, textures like breath on glass. These are lanes of dust, turning the night into a quiet play of light and concealment. Some shapes become familiar the moment you see them. Against the red glow in Orion's realm, a small cutout rises like a profile carved from paper, the horse head. It isn't a solid statue, but a dense pocket of gas and dust, so thick it swallows visible light, leaving only a silhouette. Ultraviolet from nearby hot stars sculpts its edge, peeling it back grain by grain the way wind reshapes a dune. The horse head persists for now, but the very light that reveals it is also whittling it away. Farther off, in Ophiuchus, the Snake Nebula coils through a pale star field, a dark filament that looks like smoke, paused mid-curl. Turbulence, gravity, and magnetic fields weave the gas into threads. Inside those threads, denser pockets may one day collapse into stars. The shape is both sculpture and seed, a still frame from a long story of forming suns. Dust hides and reveals in the same motion. A grain will scatter part of the light that touches it, sending a faint halo toward us and making the cool blue shimmer around reflection nebulae. The rest it absorbs, warms with, and then re-releases as infrared, a soft glow that human eyes cannot see, but infrared telescopes can read like embers in an evening fire. In this way, what looks like shadow in visible light becomes a warm sketch in the longer wavelengths, a reminder that darkness often means not here, not now, rather than nothing. There's another quiet trick. Many grains aren't perfect spheres. They're elongated or irregular. Under the influence of galactic magnetic fields, they tend to align like tiny compass needles. As starlight passes through such aligned dust, the waves of light line up a little. The light becomes polarized. By measuring the direction and degree of that polarization, astronomers can map those invisible magnetic threads that run through a cloud and across the Milky Way's disk. Dust, then, isn't only an obstacle. It is also a messenger, carrying a hint of the forces that shape what we see. For all its reputation as a blocker, dust is among the most creative materials the universe knows. Inside dense clouds, grains drift and collide at low speeds. Electrostatic whispers help them stick. Little clumps grow into bigger ones. Pebbles become boulders, and boulders given time and quiet become the beginnings of worlds. Every solid surface you've ever touched, from Earth's crust to the ice of a comet, can trace a lineage back to these tiny wanderers. The nuisance on a lens is the scaffold of a planet. Dust also lends color in subtle ways. In emission regions, dust eats a portion of the harsh light from hot stars and returns it as warmth, softening the look and deepening the glow. In reflection regions, the same scattering that blues our daytime sky favors the cool silver blues of dust clouds. In dark regions, light cannot thread the needle at all, and the result is high contrast chiaroscuro, a play of radiance and shadow the old masters would have envied. Without dust, the Milky Way would be flatter and less mysterious, a sky of uniform brightness, missing the depth that draws the eye in and lets the mind wander. Even a whisper of dust can matter. A cloud, holding only a few atoms per cubic centimeter, is nearly perfect emptiness by earthly standards, can dim starlight across hundreds of light years. If astronomers ignored that dimming, the cosmos would look unfairly faded, and distances would come out wrong. The universe sometimes wears a veil so sheer it's easy to miss, and so effective it changes everything. And still, dust is delicate. Harsh ultraviolet breaks it down grain by grain. Shock waves from supernovae shatter it into fragments. Yet even this destruction feeds the cycle. Broken pieces become seeds for new grains in cooler shadows, and the rhythm begins again, formed in old stars, reshaped by light, gathered back into the making of new systems. To a casual glance, a dark nebula might look like a hole punched through starlight. Stay with it, and you notice the shape has weight, posture, edges, where light thins and then fails. It is presence, not absence, a quiet architecture tucked into the vastness. Dust sculpts the beams we do see and guards the ones we don't, turning the universe into a gallery of living shadows. The next time an image shows a crimson bloom, a blue haze, or a black cutout against a field of stars, remember how much of that beauty depends on the tiniest things. One grain can change the path of a photon. A handful, spread across a light year, can change the face of a region. A ribbon of grains, stretched for dozens of light years, can rewrite a sky. Among all the glowing folds of the night, few places feel as familiar as the Great Orion Complex, a neighborhood of creation sprawling across hundreds of light years. Gas, dust, and newborn stars work together there in a workshop that never quite sleeps. Even without optics, winter evenings betray its presence. 3 bright points form the belt. Below them hangs the sword, and within that sword, a small patch of mist glows. That blur is the Orion Nebula M42, one of the most active star-forming scenes in our part of the Milky Way. Orion's realm is not a single object, but a family held together by gravity and shared history. Dark clouds, bright emission regions, arcs of expanding gas, and faint curtains linked by the push and pull of radiation and wind. The grandest arc is Barnard's Loop, a vast crescent that sweeps around the constellation. If human eyes could register its faint red, it would stretch across more than 20 full moons worth of sky, a long bow framing the hunter. Many think it is the echo of an ancient event, either a supernova or the collective breath of massive stars that lived quickly and were done its curve tracing the boundary of a giant bubble carved into the interstellar medium. Inside that bubble, new stars find room to begin. Toward the center, the gas grows denser and the light grows bold. There, a giant molecular cloud is folding in on itself under gravity's patient hand, turning knots into clusters and clusters into small, brilliant suns. The 4 brightest lamps at the core make the trapezium, a tight group whose ultraviolet pours outward and floods the region. Those few stars, only a few million years old infants by stellar standards, are already shaping everything around them. Their radiation clears a cavity at the nebula's heart, heating and pushing away the very material that once sheltered them. It looks like destruction because walls are coming down, but it is also construction, because the pressure waves that sweep outward compress other parts of the cloud and coax new collapses. The region behaves like a self-sustaining workshop, the young tearing through the old to make room for the younger still. That violence is precise rather than wild. Stellar winds carve pillars and ridges. Ultraviolet light trims their tips into rounded caps that glow. Fingers of gas point back toward the sources that sculpted them. It's a patient storm, loud in energy but quiet in sound, because there is almost no air to carry noise. The shapes shift over tens of thousands of years, which on the scale of star birth is a quick flicker. Around the trapezium, smaller treasures crowd the scene. Hundreds of faint, tight ovals and crescents dot the glow. Astronomers call them proplyds, short for protoplanetary disks. Each one is a dusty cocoon circling a newborn star, a seedbed for rocks, then worlds. Some appear as dark almonds silhouetted against the bright background. Others shine at their edges where radiation etches them. You are looking at sketches of solar systems in rehearsal, their scripts still being written by dust and gravity. In such places, grains stick, pebbles gather, and invisible hands begin to measure orbits in the language of time. Part of the reason Orion teaches us so well is how close it is, around 1,300 light-years away. Close enough that details come through with clarity. Every wavelength has been turned on the region. Visible light shows the deep red of hydrogen emission, a cool wash of oxygen's pale green, and the faint blues where dust scatters starlight. Infrared reveals the warm cocoons hidden by dust, younger stars still swaddled in their first blankets. Radio maps the cold molecular gas, the raw material waiting its turn. Each layer is a page in a notebook. Taken together, they trace a process rather than a picture. The beauty of Orion is how many pieces talk to each other. The loop's expansion nudges gas that will feed the nebula. The bright nursery's winds and lights send ripples that squeeze nearby regions. Just to the side, the Horsehead and the Flame Nebula share the same broad reservoir of material and respond to the same energetic neighbors. Red from hydrogen emission, blue from scattered starlight, black from dust lanes, each is a sentence in the same language of change. Stand back, and the region feels like a single heartbeat heard through many stethoscopes. All of this would read as pure science if not for the way Orion has trailed its stories through human memory. People have looked up and found a hunter's shape for thousands of years, telling myths of strength and pursuit. They could not have known that behind the pattern was a nursery, a place where matter learns the steps that will become mornings. The old figure promised endurance and power. The nebula offers a gentler truth. Creation and unmaking share a boundary. Light is born at the edges of darkness, and new beginnings are always forming in cold, quiet corners. On a clear winter night, if you step outside and let your eyes adjust, the belt shows first, and below it, that misty patch wakes. You may be standing in your yard or on a balcony, but the light reaching you began its journey before the first cities on Earth grew their own glow. It crossed more than 1,000 light years to arrive in this moment. In that small fan-shaped haze that a pair of binoculars will turn into a luminous wing, you are seeing a workshop in motion. Dust scattering blue at the edges, hydrogen singing in red deeper in, young suns pushing cavities into their cradle, and small disks where worlds are practicing their first slow turns. It is tempting to think of all this as decoration hung in the sky, posters in a gallery we visit with cameras and telescopes. The truth is more intimate. Dust sets the terms for what can be seen, yes, but it also sets the terms for what can be made. It is a muffler and a midwife, a painter and a chisel, a record and a roadmap. It dims a star just enough that we misjudge a distance, unless we remember to account for it. It cools a cloud just enough that gravity can finish its gathering. It breaks and rebuilds, shatters and starts again, a patience measured not in years but in the steady way. Small things insist on mattering. Think of a single grain, a shard of silicate, or a carbon flake, smaller than a red wavelength, drifting for 10 million years. It feels a supernova's shock and fractures. Later, in a cooler shadow, it grows a thin coat of ice. Later still, it slides into a newborn disk around a star. It collides gently, sticks, and becomes part of a pebble. That pebble finds others. Numbers become mass. Mass becomes a body. The body clears a lane and calls it orbit. And one dusk, far in the future, light will shine from a sky onto rock that once was a speck, and someone on that rock may lift their face and wonder at a pale band arcing overhead. When you look at Orion or any nebula and feel that bright ache of beauty, you're sensing the balance dust keeps, hiding and revealing, cooling and warming, breaking and building. The cosmos isn't painted by light alone. It's carved by the smallest shadows. Dust takes starlight and turns it into sculpture, gives emptiness a contour, and lets the universe speak in contrasts gentle enough to cradle sleep and firm enough to hold meaning. In that hush where contrasts gather, the making of worlds goes on grain by grain, faithful to the slow rhythm that keeps everything becoming. Follow that balance from the idea to a place you can point to in the sky. Near the bright eastern jewel of Orion's belt, two neighbors keep different kinds of quiet, the Horsehead Nebula and the Flame Nebula, close to Alnitak, like opposite moods in the same night. One is a silhouette so dark it feels cut from the sky. The other, a soft blaze, all ember and glow. Together, they show how dust and starlight sculpt the same cloud in reverse, one by refusing light, the other by letting light find its voice. The Horsehead, catalogued as Barnard 33, isn't a single object in the way a mountain is a single stone. It's a dense column of cold gas and dust, standing in front of a luminous backdrop called IC 434, a red curtain of hydrogen lit by ultraviolet from a nearby massive star, Sigma Orionis. Against that gentle radiance, the profile appears, neck arched, muzzle lifted, the curve of a mane suggested by thin folds and darker strands. It feels sculpted, but it's an accident of perspective and time, the universe sketching something our minds are ready to recognize. The blackness isn't emptiness, it is fullness, grains thick enough to catch or scatter nearly every visible photon that tries to pass through. The gas is only a few dozen degrees above absolute zero. Inside, gravity is quietly gathering clumps that may one day warm and ignite. At the edges, light does its slow work. Ultraviolet radiation nibbles the outline, heating, evaporating, and carrying gas away. Along that border, a thin halo appears, the soft seam between shadow and dawn. The head itself looks tiny to the eye, barely a thumbprint at arm's length, but it rises several light years tall, large enough to swallow our solar system again and again. For all that size, it remains fragile. Radiation is patient. Grain by grain, the shape is being sanded down. In a few million years, the horse will fade back into the mist that made it. Not far away on the same stretch of sky, the Flame Nebula, NGC 2024, burns beside Alnitak. Where the horse head withholds light, the flame releases it. Ultraviolet from Alnitak strikes nearby hydrogen, strips electrons loose, and then, as those electrons fall back, the gas glows in deep red. In the bright core, oxygen and nitrogen add faint greens and blues, layering the light so that long exposures look like a candle in still air, base dark, edges feathered, center alive. The dark lanes that slice through the bright face aren't voids, they're cooler dust laid across a lamp. Magnetic fields and stellar winds thread those filaments into curves and ribs. In infrared, astronomers find clusters of young stars hidden inside, newborn suns that visible light can't reveal because dust veils them. The warmth slips through anyway. In that way, the flame is both a theater and a nursery. The glow you can see, and the beginnings you can't. The physics beneath the beauty is steady and kind to understand. Gas glows when electrons return home after starlight has thrown them into motion. Ridges and folds appear where pressure, wind, and magnetic lines guide the flow. What looks like flicker is really a blend of countless small lights spread across dozens of light years. Along the edges, bright fronts mark the boundary where ultraviolet meets unlit hydrogen ionization fronts, thin veins of transformation that show how light doesn't just reveal a scene, it remakes it. Place the horse head and the flame together, and you can read the two sides of that remaking. One shows dust standing its ground, holding brightness at bay. The other shows light pushing back, changing chemistry and temperature as it advances, creation and erosion, concealment and revelation, stillness and energy, all in one glance. It's easy to mistake the pair for deliberate artistry. The horsehead looks like a single stroke of ink, the flame like a wash of color laid beside it. In truth, waves of pressure, radiation from massive stars, and the soft pull of gravity have been working for millions of years to find these contours. The resemblance to a horse is a kindly trick of perception. We are pattern seekers. Early photographs at the end of the 19th century captured that silhouette, and the astronomers who made them felt what anyone would feel, a sudden, familiar shape where none was expected, as if the universe had gone out of its way to speak clearly. Modern images deepen the enchantment. You can trace wisps curling like hair along the mane, follow the pale rim where erosion glows, and in the flame, see filaments etched like smoke veins through a hearth. The sensation is the same now as then, science and beauty sharing a lamp. For observers with small telescopes, this neighborhood rewards patience. The flame can appear as a faint patch near Alnitak under dark skies, its glow softened by the star's brilliance. The horse head is trickier, shy, and subtle, usually needing a filter that singles out hydrogen's deep red to let the silhouette stand out, but even knowing they are there changes how Orion's belt feels. Behind the bright three-pointed line lies a world made of shadow and fire, dust standing at the threshold of dawn, and light writing warm signatures into gas. Far from Orion, another scene has become a lantern for anyone who loves these quiet factories of light. In the Eagle Nebula, cataloged as M16, stand the pillars of creation, columns of gas and dust rising like weathered stone, each several light years tall. The name is poetic and precise at once. Inside those columns, baby stars are forming. Around them, harsh radiation is constantly trying to tear the structures apart. From a distance, the place seems calm, pillars floating in a golden haze, newborn stars scattered like small, bright seeds. In truth, the region lives inside a storm. A cluster of massive young stars floods the area with ultraviolet light strong enough to ionize gas and with winds powerful enough to carve enormous hollows. The pillars are what remains where the cloud is densest last standing shapes resisting the push, even as the outer layers are warmed and carried away. That eroding skin has a name: photoevaporation. It's why the edges look so sharply drawn. Invisible winds sand them down over thousands of years, thinning their outlines one atom at a time. Radiation striking the tips creates bright ridges and shock fronts that travel downward through the columns, compressing gas as they go. Compression can trigger new collapses. In that way, old stars help make new ones, using the very forces that will later erase the nursery walls. Creation and destruction travel together here, not as enemies, but as a cycle. The pillars stepped into public imagination in 1995 when the Hubble Space Telescope photographed them in visible light. 3 great fingers, tinted in golds, blues, and greens, rising out of a lake of glow. The image became a shared language for star birth, pinned to classroom corkboards and taped to bedroom walls. Not because it was the most colorful thing the sky could offer, but because it made a process visible. Years later, the James Webb Space Telescope looked again, using infrared. Where Hubble showed surface and texture, Webb showed temperature and interior. Infrared can slip through dust, revealing stars hidden within the columns as tiny, warm points. In those views, the pillars look more translucent, almost lit from inside, as if the mist itself had decided to glow. Together, the 2 portraits feel like layers of the same painting, one for the skin, one for the bones. What's revealed in both is the complexity of feedback. The massive stars at the heart of the Eagle Nebula create and dismantle in the same breath. Their radiation compresses some pockets into future stars while sweeping others away. The bright cavity around the pillars is filled with gas heated to thousands of degrees, expanding like a slow-motion blossom. Its edges are the sculpted walls we see, the living boundary between what was and what is becoming. To us, the scene looks frozen. To the cloud, it is changing all the time. A single pillar may last only a few 100,000 years before it's erased, a brief moment on a galactic clock. Yet the stars born inside will shine for billions of years after the pillars are gone. It's an old lesson whispered gently. Temporary things can still make lasting gifts. The Eagle Nebula lies roughly 7,000 light-years away in the direction of Serpens. The central cluster, NGC 6611, is only a few million years old, a handful of seconds if the galaxy's life were squeezed into a single year. In those few seconds, hundreds of stars have already come to be, each with the potential to gather a family of planets. And the pillars are only one set of shapes in a much larger weave: arches, knots, globules, each a memory of how radiation and gravity have negotiated their truce. Some forms are just beginning, some are fading, some have already caved into clusters, the room swept clean where a nursery once stood. From an artist's distance, the pillars look invitingly solid, as if you could climb them. Up close, they are almost nothing, gas so thin that a cubic meter would hold fewer particles than the best vacuum on Earth. Yet that near nothingness is capable of astonishing work. Inside, small pockets of density collect and round themselves into spheres. As they collapse, they heat. As they heat, they begin to glow. And one day, they ignite. The universe takes something you cannot grasp and makes it a sun. If you could stand still for millions of years and watch, the Eagle Nebula would seem to breathe. New stars would flare on. Waves of radiation would sweep across the cloud. The pillars would shrink and crumble and finally dissolve. An open cluster would take their place and hang in clean space. The light that reveals them now will eventually erase them. This is how star-making goes. Beauty, born from impermanence. Endings that behave like beginnings when you zoom out far enough. The story, written in these shapes, is not limited to one nebula. It's the way light, gravity, gas, and time talk wherever stars are forming. Light knocks electrons loose and writes color on the airless dark. Gravity gathers what's loose, tightens it, and holds it to a new center. Winds push, magnetic lines guide, pressure waves pinch and release. The result is both predictable in principle and astonishing in detail. The same physics repeating, yet never quite making the same pattern twice. When the famous image of the pillars finds you again on a screen, on a page, in a memory, let it be more than a picture. See it as a single frame from a long, ongoing film. Somewhere inside those columns, small suns are quietly taking their places. Somewhere outside, intense light is gently taking the walls apart. The balance between the two is temporary and beautiful. And if you step outside on a winter night and look toward Orion's belt, letting your vision rest near Alnitak, imagine that in a different corner of the galaxy, a similar dance is going on. A silhouette, standing, a flame unfolding, dust deciding where light may go. These scenes have traveled a long way to find you. The light you see left its home before the first great cities glowed bright enough to fade the constellations. It has crossed hundreds, even thousands of light years to arrive now, carrying in its waves the faint red of hydrogen, the pale green of oxygen, the soft blue of scattered starlight, and the deep black where dust keeps its secrets. Behind the familiar shapes, hunters, eagles, horses, the universe continues its quiet labor, raising pillars that will someday vanish, lighting flames that are really atoms, exhaling after collision, sketching a horse's head from coincidence and structure intertwined. It is a gallery of opposites where nothing contends. The glowing gas and the dark dust do not compete, they complete each other. From energy and stillness, concealment and revelation, the sky builds a truth that feels whole. And farther south, beneath the bright river of the Milky Way, another masterpiece unfolds. The Carina Nebula, NGC 3,372 moves like weather made of light, immense and alive, vast enough to swallow Orion many times over. If the night were a painting, this would be the wild place where the brush caught fire and refused to stop. Nothing here rests. Radiation floods outward from clusters of young, hot stars. Winds of charged particles race at thousands of kilometers per second. Heat presses on every curve of gas until it glows. The whole expanse breathes bright, turbulent, and strangely serene, a storm wrapped in calm, unfolding at the pace of eternity. At the center of this restless country stands a star with a biography, Eta Carinae, spoken of with both awe and caution. In the mid-1800s, it flared in what we now call the Great Eruption. For a time, it became the second brightest star in the night, not because it died, but because it shed several suns' worth of mass, throwing off a pair of lobes now known as the homunculus nebula, an hourglass glowing inside the larger Carina complex. That outburst spattered the neighborhood, stirring gas, carving layers, and compressing knots until some of them collapsed into new stars. It was violence that behaved like a gardener's hand, rough and generous at once. Eta Carinae is still unstable, a brilliant warning light on the edge of change. One day, it will likely end in a true supernova, a brief lighthouse so bright it could outshine the galaxy for a moment before slipping into memory. Even so, Carina is bigger than one fate. Think of it as an ecosystem, thousands of stars at different ages, their outputs overlapping, their winds colliding, their light shaping the same vast cloud into ridges, cavities, towers, and veils. Where flows meet, shock fronts rise. Thin walls of compressed gas glow in intricate filaments. Arcs bend like sculpted ribs, and long pillars stand where dense material resists. Astronomers have a plain phrase for all this turbulent feedback, but standing before the pictures, the word weather feels closer. There's no sound, no air for that, but the motions rhyme with storms we know, spirals where currents twist, broad fronts sweeping through, calm pockets forming in the lee of something bright. The contradiction is part of the beauty. The same ultraviolet photons that set hydrogen ringing in reds and pinks also erode the edges of the cloud that feeds star birth, chipping it into lace and streaming tendrils outward into interstellar darkness. Creation and unmaking touch the same place at the same time, like two hands at one wheel. Through all this run magnetic fields, unseen threads that matter likes to follow. Grains align with them, charged gas flows along them, filaments braid where the lines twist. Those braids are not random decoration. They are the fingerprints of order, inside chaos, balance, hiding in motion. Without magnetism, Carina might be only a grand blur. With it, we read patterns that suggest intention, even where there is only physics. Long cords arcing for light years, knots where the cords tighten, windows where the pattern opens. The energy budget of this place is enormous. Central clusters pour out enough light to ionize gas across hundreds of light years. Winds carve entire cavities. The material they sweep piles into shells, and at the rims, pressure climbs. Gravity finds leverage. New stars begin. Layers of birth and decay stack like geological strata, a record you can't hold but can trace with your eyes. In images, hydrogen paints crimson, oxygen contributes cool teals, sulfur leans orange. Between those glowing curtains lie dark pockets where dust thickens. Light can't yet enter, and gravity keeps its own counsel. Those are the quiet corners in the storm, the wombs of futures. From a distance, Carina can feel like a symphony arranged for color and time. Stars pulsing, gas humming in emission lines, shock waves beating softly. The whole score stretched over millions of years, so that what is violent in principle becomes meditative in practice. The scale slows everything down for us. What might be chaos up close becomes composure from here. It is not so different from looking at ocean surf from a cliff-white energy below, steady breath above. There's a humility tucked in these folds. Billions of years ago, our own sun began in a place like this, one cloud among many, siblings around it, ultraviolet washing the scene. The steps happening in Carina, compression of gas, carving of cavities, the collapse of dense cores, are the same steps that once wrote our beginnings. People sometimes call Carina Orion on steroids, but the joke undersells it. This is a whole weather system, a continent of feedback, from tiny knots warmed from within to world-scale arcs spanning hundreds of light years. Power is everywhere, and yet the scene leans toward calm. Waves of light, soft-edged folds, even explosions stretched into gentleness by time. Creation doesn't hurry. It works steadily, and sometimes it sings while it works. Carina will fade one day, gas will disperse, massive stars will die dramatically, and the remaining light will thin. For now, it stands as a portrait of cosmic weather caught in mid-motion. Bright ridges like lightning fixed in place, magnetic currents like wind you can't see, and the faint promise of stars forming in the deep interior where no visible light can go. A storm that hushes as it moves, proof that force and grace are not opposites here. Turn toward Sagittarius, where the summer Milky Way arches brightest, and a different duet waits the Lagoon Nebula, M8, and the Trifid Nebula, M22. Clouds on the same canvas, distinct in character, close enough in the sky to share a frame from Earth. Together they compose a watercolor of warm reds, cool blues, and velvet black, a quiet lesson in how light speaks with dust. The lagoon is the broader voice, more than 100 light-years across, red with the glow of ionized hydrogen. It's an H2 region, a factory buzzing with star birth. In its core sits NGC 6530, a cluster of hot, energetic suns whose ultraviolet floods the surrounding gas, stripping electrons and letting atoms release deep red light as those electrons fall back into place. Through a small telescope from dark country, the lagoon looks like a pool of pale brightness rimmed with shadow, its name given by the impression of a luminous waterline edged by dark lanes. Long exposures show folds and filaments, the way a long shutter catches waves mid-curve. Near the center, a bright knot appears, the Hourglass Nebula, not the planetary nebula of the same nickname, but a pocket within M8 where very young stars are emerging from cocoons. The light they pour into the gas makes the region look molten, as if a fire were burning behind a thin wall. The work here is never still. Winds from newborn stars push outward and excavate cavities, while the push itself compresses neighboring regions, starting new collapses. Disturbance begets creation. Peace comes later. The lagoon wears tranquility like a veil, but underneath it, pressure and motion keep the cycle going, a slow, faithful beat measured in millions of years. Just above sits the Trifid, smaller, intricately arranged, and perfectly named. Dark lanes slice the bright face into 3 distinct lobes, sometimes 4, depending on the angle, like flower petals, divided by ink. Those lanes are not empty. They are dense ribbons of dust placed between us and the glow. The Trifid is a tidy showcase because it's 3 kinds of nebula in one. Emission in the core, hydrogen shining red, where gas is energized. Reflection in the halo dust, scattering nearby starlight into a soft blue, and darkness cut through the whole dust again, this time blocking rather than reflecting. A compact demonstration of how clouds behave, glowing, reflecting, concealing. At the center, a newborn cluster, dominated by a single strong star, shapes the region. Its ultraviolet keeps the inner gas lit while its pressure nudges dust outward, creating a layered look that feels 3-dimensional. Through a telescope, the core can seem to shimmer, red and blue, overlapping into lilac, like pigments blending on a painter's palette. The pair sing well together. The lagoon's red breath provides warmth and scale. The Trifid's blues and dark lanes add structure and contrast. Though they appear neighbors, they are separated by thousands of light years. Chance lines them up from our point of view so that a wide-field image can hold them both. That luck becomes a tutorial. In one glance, you see what hydrogen does, how dust scatters blue, how dense clumps erase the background. Color is not decoration here. It is a record. Hydrogen writes in red. Dust mirrors blue. Where dust becomes thick enough, it writes in black, a letter made of absence. These regions change, just slowly. The massive stars in the lagoon will age quickly. In a few million years, some will detonate as supernovae, sending shock waves outward. Those waves will race through the neighborhood and may compress the Trifid's outskirts, lighting new sparks of star formation. Eventually, both clouds will thin. What remains will be clusters of bright suns drifting apart along the galaxy's arms. Tonight is only one frame in that long, elegant film, a moment when light, dust, and gravity share a temporary balance. For anyone under a dark sky with binoculars, the lagoon is a reachable treasure, a soft smear in the crowded heart of the Milky Way. The Trifid is fainter, but a modest telescope will make its trilobed shape apparent, dust lanes cutting like fine calligraphy through the glow. Knowing what they are, the scale of them, the chemistry made visible deepens the quiet. These are regions hundreds of trillions of kilometers across, and yet their physics is the same physics at work in a candle's flame or a breath on a window. Electrons falling back into place, light bouncing from tiny grains, matter warming and cooling with the smallest push. The elements are familiar: hydrogen, oxygen, carbon, sulfur, the same alphabet found in your blood and bone, your water and air. What these scenes share, from Karina's wild weather to the lagoon's calm pool and the Trifid's precise geometry, is a simple truth about contrast. Where dust and light meet, color blooms. Where darkness intrudes, shape is born. Gravity gathers, radiation sculpts, magnetic fields guide the hand. Beauty in space isn't an accident or an extra, it's the visible edge of laws playing out at their natural scale. Look long enough, and the patterns begin to feel personal, not because the universe bends toward our meanings, but because we are built from the same processes and recognize their signatures in our own ways of seeing. There is comfort in that thought. Karina's bright ridges and hidden winds, the lagoon's hourglass glow, the Trifid's soft petals of shadow, each one a chapter in the same long tale of clouds learning to shine, then thinning into clusters, then drifting apart to seed new clouds elsewhere. Even Eta Karine's great outburst, fierce and extravagant, becomes part of the larger calm when you step back far enough, an eruption that destroys and nourishes at once, proving that endings and beginnings can share the same breath. When you stand beneath the stars and trace Sagittarius or follow Orion's belt, the light that meets your eyes began its journey long before cities dimmed the sky. It traveled across distances that outlast whole civilizations, carrying messages written in color and contrast. Hydrogen's blush, oxygen's cool glow, the black quiet where new suns are forming. In that unhurried conversation between light and matter, the universe both works and rests, sculpts and softens, breaks and repairs. The rhythm is slow, the tone is gentle, and the meaning is constant. From the tug of simple forces, grace emerges and keeps emerging until even chaos looks serene. from the right distance. Some clouds seem to understand that serenity. They lean toward symmetry, as if calm hands had shaped them. Two such clouds rest on that quiet edge: the Rosette Nebula, round and blooming, and the California Nebula, long and drifting like a red ribbon through the dark. One gathers your gaze inward, the other invites it to wander. If the Milky Way were a vast kitchen, one would be a perfect ring, just lifted from the oven, the other a soft loaf, cooling slowly on the counter, both made not of flour and heat, but of hydrogen, dust, and time. The Rosette cataloged across NGC 2,237, 2,246 flowers in Monoceros at roughly 5,000 light-years, its wide petals 100 light-years across. The color that reaches us is the deep blush of hydrogen alpha. In the center sits NGC 2,244, a young cluster whose hot, bright stars do the lighting and much of the sculpting. Their ultraviolet shakes electrons loose. Their winds sweep. Together they have excavated a hollow, where the cluster now shines almost naked to space. What remains is a shell, a classic H2 region ionized gas ringing the emptied center like a lantern's shade. The form feels intentional, but it's only the natural geometry of pressure and flow, the way light, motion, and gravity can agree on a round solution when given a little time. Inside the ring, the gas thins, giving a clear view to the cluster's bright points. The stars keep pushing. Warm, ionized gas drifts outward until it finds an opening in the shell and pours through in a smooth, steady stream. Astronomers call it a champagne flow, an image that fits, pressure seeking relief, then expanding with elegance. In that slow escape, you can watch a cloud change state from dense and private to airy and shared on scales too large for urgency. The Rosette is a moment in the middle of transformation, balanced between a busy molecular nursery and the eventual clarity of open space. The ring will fade. The cluster will relax and drift. The bloom will become a memory threaded through new stars. For now, its symmetry is a lesson. Feedback does not need fireworks. It can be patient and neat, a long conversation in which the push of light and the pull of gravity find a temporary truce along a luminous edge. Those edges glow in hydrogen alpha, tracing a boundary as fine as breath on glass ionized interior, within colder molecular gas without. The uniformity is not stiffness, it's peace. Many small irregularities still live on the rim, little knots, pillars, and bays, places where gravity has a say, where dust thickens, where a future star might gather its first threads. Even in a ring, the universe keeps its fondness for variation. Across the sky, the California Nebula NGC 1499 rests in Perseus like a beam caught in fog. Photographs run a familiar outline along its backbone, the state's shape written in red light. Here, a single star, Xi Persei, Menkib, an O-type beacon, does most of the work. Its ultraviolet pours into a loose, elongated cloud, ionizing hydrogen along a path nearly 100 light-years long. The result is gentler than the Rosette's bold ring, a smooth gradient of brightness, blush deepening to pale, then blending into dark, where dust threads through, faint blue and violet shimmer from scattered starlight. Where gas is thickest, hydrogen carries the scene. Simplicity is part of its charm. The California is not a cathedral, it's a river. No central hollow, no grand bowl, rather a slow exhalation guided by geometry and chance. The same physics drives it: ionization, recombination, scattering, but the canvas is different. One strong source, one long cloud, a steady hand. Within that glow, ultraviolet light helps write chemistry into the cold. Molecules break and form. Carbon and oxygen trade partners. Dust grains grow or shed coats of ice. The changes are modest in any instant, but over time, they tilt the balance, deciding what kind of dust survives, what molecules linger, what futures are favored when gravity comes calling. Quiet alchemy, done in the dark between stars. Side by side in thought, the Rosette and the California show two faces of stellar feedback. In one, many stars act together, pressure swelling the interior, building a shell, opening a vent, and letting the warm gas sigh outward. In the other, a single star extends a lane of light through an easy cloud, energizing gas along its drift. The ring feels architectural lines resolved, spaces intentional. The ribbon feels natural curves that seem found rather than built. One draws the eye inward, the other draws it along. A circle and a road, a bloom and a breeze. Both reward patient eyes. Under a dark sky, the rosette can be found as a faint, round haze, with a cluster bright in the middle. A hydrogen alpha filter brings out lacework, as if frost had set on the rim. The California prefers wide-field cameras and slow exposure. Its light too spread to concentrate in a small eyepiece. A photograph reveals textures you wouldn't guess were there, gradients as soft as smoke fading into night. In both, the lesson is the same. Light paints faithfully. Red writes hydrogen. Blue arrives when dust scatters nearby starlight. Black is not emptiness, it is presence, dust thick enough to hold the background at bay. Shadow has its own catalog of beauty. Not every wonder announces itself in glow. Some lie in the places where the sky seems to fold inward, dark nebulae, the quiet counterparts of the showy H2 regions. From a distance, they look like thumbprints pressed into the Milky Way, edges soft, interior pure night. But the darkness is fullness, cold gas and dust, dense enough to stop visible light. If a bright nebula is a lantern, a dark one is the shade letting shape appear by what it hides. Dust grains inside these clouds drink blue and ultraviolet efficiently. Stars behind them redden and dim. The darkest patches go altogether black to the eye. These silhouettes mark where the galaxy stores raw material for future light. In the south, near the Southern Cross, the coal sack is the best known of these shapes, a broad void cutting into the Milky Way's bright band. To many indigenous Australians, the dark marks the head of the emu in the sky, whose body is traced by other shadows down the river of stars. Its position in the seasons serves as a calendar, a guide for life on the ground. Early European observers labeled the region a black nebula, marveling at a presence that looked like absence. Infrared cameras and radio telescopes later showed what the eye could not: a cold molecular cloud roughly 600 light-years away and about 70 light-years across. Its temperature only a few degrees above absolute zero. Inside, molecules such as carbon monoxide and ammonia form, protected by dust from the harsh light outside. Along the edges, faint infrared glows reveal dust warmed by hidden stars. Deeper in, radiation is scarce, collisions are rare, and gravity takes its slow chance. Small knots gather, densities rise. Somewhere, quietly, a core will cross the threshold. heating as it collapses until fusion begins, a first light born out of deep shade. Elsewhere, in Ophiuchus, Barnard, 72, the Snake Nebula draws a clean line, a black filament curling across a rich star field. It looks hand-drawn, the contours so specific you might suspect art. The darkness again is matter, a narrow, cold strand, only a few light-years wide but long enough to thread a slice of sky. Magnetic fields and turbulence likely helped arrange the filament. Gas in the Milky Way loves to gather into threads, and threads feed dense knots, and knots invite stars. In far infrared images, tiny warm points peek from within the serpent's hidden eyes, protostars still wrapped in dust. Visible light refuses to show them. The longer wavelengths tell a different story. Radio lines from molecules trace the flows, map the arteries. Infrared heat reveals cocoons. Astronomers rebuild the hidden architecture, filaments, knots, cores, and watch the roles of turbulence, gravity, and magnetism interleave. Inside such clouds, the extremes are soft. Temperatures hover near the cosmic minimum. Pressures are low. Motions slow to a human kind of metaphor. Hundreds of meters per second, rather than thousands of kilometers. Collisions are infrequent, but time is generous. Molecules grow on the surfaces of dust grains, step by quiet step, building the chemistry that will one day flavor atmospheres and rivers on worlds not yet drawn. These are the kinds of rooms that once held our sun's beginning. To look at a dark nebula is, in a way, to look at the rough draft of home. Edges matter here. A dark cloud's boundary often glows faintly, where starlight grazes it, a suggestion of contour. Filaments curl where a passing shock tugged on dust. Strands thin and split under magnetic tension. Globules pinch into teardrops. Their pointed ends, aimed at the nearest bright star, the mark of light's pressure over time. Shape changes slowly, but it does change. A filament can disperse and be gone. A globule can collapse and then no longer count as cloud, but as cluster. The studio empties after a masterpiece is finished. The light moves in where shadow once worked. Absence gives brightness its meaning. Without a context of dark, even the richest glow would feel flat. The coal sack's wide curtain and the snake's precise meander teach the same quiet. The galaxy uses shadow as scaffolding. It gathers, it cools, it waits. The waiting is not emptiness, it is preparation. When the time is right, a part of the dark will turn to light slowly, then all at once, until, from far away, someone sees a new patch in a new sword in someone else's winter sky and feels their breath slow with the sight. Return for a moment to the rosette's tidy ring and the California's long whisper. The pair make an easy parable. One curves inward, a bloom protecting the cluster it raised even as it lets gas escape along the cleanest line. The other stretches outward, a beam tracing where a single star reaches. They are both built by the same small set of tools: pressure, radiation, motion, gravity, magnetic order applied at different angles. In one place, many hands; in another, one hand in a generous sweep. Neither is hurried. The rosette took millions of years to find its equilibrium. The California shines by a steady companionship between star and cloud. They remind us that the universe often prefers patience over spectacle, that steady light can make forms as striking as any blast. And the dark companions, the coal sack, the snake, remind us that beauty can be true in silence. A lampshade can be as lovely as a lamp, especially when you notice the pattern it throws. Behind every bright nursery are rooms like these, cold, guarded, busy and secret. The bright names, the Orions, the Carinas, the lagoons are exhibits. The dark are studios. Together, they show the full grammar, vowels of light, consonants of shadow, words spelled across hundreds of light years. A poem you read by letting your eyes adjust. Under a good night, binoculars will find the rosette's faint bloom with the cluster like a jewel at the center. A small telescope and a hydrogen alpha filter will soften the ring into lace. Wide field photographs give the California room to stretch. Long exposures pull its smooth gradients from invisibility. The coal sack needs nothing but southern sky and attention. The snake asks for a telescope and a steady look. In each case, what you're seeing is simple physics, played on a large stage, electrons falling back into place, dust turning light aside, gravity shaping breath into structure. The elements are familiar. Hydrogen's red, dust's blue, scattering darkness where density wins. The patterns feel familiar too, perhaps because we are built from the same pieces, tuned to the same quiet patience. Every star begins as a hush inside the dark, a faint thickening in a cold cloud of gas and dust. From the outside, nothing seems to stir. The cloud drifts dim, unremarkable along the Milky Way's slow lanes. Deep within, gravity has already started its patient work. Over long, quiet ages, that invisible pull gathers atoms into a denser breath. Pressure creeps upward. Warmth kindles molecule by molecule. Described calmly, it sounds like nothing more than settling. In truth, it is one of the universe's most astonishing transformations. Light emerging from darkness. It begins with small differences. A giant molecular cloud is never perfectly smooth. Tiny variations in density, temperature, and magnetic fields give some patches just the slightest advantage. Those patches pull a little more material than their neighbors. More mass means more gravity. More gravity means more mass still. The once even mist fractures into fragments, seeds a few light years apart, that outline the bones of a future cluster. Within each fragment, gathering continues. The gas contracts and warms as particles bump more often. A compact core forms, cold by earthly standards, only 10-20 degrees above absolute zero, yet warmer than the space that swaddles it. Becoming opaque to its own radiation, the core traps heat and slows its fall, like a deep breath held for a long time. Spinning begins as a consequence, not a command. Nothing in the cosmos is perfectly still. Even a cloud, with almost no rotation, carries a flicker of angular momentum. As the cloud shrinks, that little spin intensifies the figure skater, drawing arms in, turning faster without trying. Rotation refuses a perfectly spherical collapse, so the infalling gas flattens into a disk that orbits the center. It is an elegant compromise. Gravity pulls inward, rotation spreads outward, and the accretion disk forms between them, both funnel and brace. Through that disk, matter threads toward the heart steadily enough that the system doesn't tear itself apart. At the center, something small and hot emerges, a protostar cocooned in dust thick enough to hide it from ordinary sight. As gas spirals inward through the disk and lands on that infant surface, the fall releases energy, warming the core until it glows in infrared. Human eyes can't see it, but the right instruments can. A red warmth in a black room. This phase is slow and balanced. Hundreds of thousands of years may pass while the protostar feeds. Gravity draws in, inner pressure pushes back, rotation keeps time with both. The balance rarely stays polite. As the protostar grows, magnetic fields anchored in the spinning disk and star twist tighter, then launch narrow jets from the pole's bipolar outflows that carry material and angular momentum away. They gush into the surrounding cloud for light years, glowing faintly where they ram into the gas, riding symmetrical streaks and bow shocks across the dark. Think of them as relief valves and sculptors at once. They prevent the infant from spinning itself to pieces and stir the neighborhood into patterns, compressing here, clearing there, so that new collapses begin. One birth nudges another. The nursery grows busier. Inside, the temperature keeps climbing. When the core reaches roughly 10 million degrees, the quiet threshold is crossed. Hydrogen fuses to helium. The energy released pushes outward with enough strength to balance gravity's pull. Collapse halts, and a steady state settles in. The protostar becomes a star in the real, formal sense, no longer shrinking, not yet dying, just burning softly in its new radiance. Around it, the disk thins. Most of the gas either accretes onto the star or is blown away by stellar winds. Heavier dust remains, bumping and sticking, growing from grains to pebbles to rocks. Swirls of material carve lanes and rings. Gaps appear where young worlds start to gather their orbits. The same steps that once shaped the sun and earth are happening again and again across the galaxy. Every quiet point of light overhead is a success story, a fragment that collapsed, a core that ignited, a fusion fire that took. From cold cloud to stable star can take a few million years. For us, that's a forever. For the galaxy, a blink. Some stars hurry massive, brilliant, destined for short, dramatic lives. Others take their time and then keep time well, burning gently for billions of years. The path depends on mass and environment. The steps repeat. Gravity gathers, heat builds, fusion begins, light joins the sky. Each new star inherits a history. The gas and dust that feed it carry traces of almost everything that has happened before. Oxygen and calcium from long-dead supernovae, carbon from red giants, silicate dust from older systems. Anything heavier than helium was forged in stars that lived and ended earlier. When a molecular cloud collapses, it is recycling, folding old stories into new ones. A newborn star is both an ending and a beginning, a last chapter for the atoms it gathers, a preface for the worlds those atoms may someday make. Not every dawn is gentle. Some infants flare and flicker. Some jets carve stronger marks, yet all begin the same way, as a soft increase in density in the cold. The universe builds stars the way wind shapes dunes, slowly, persistently, one particle at a time, until a line becomes a ridge and the ridge glows in low sun. As stars live, they spend long, quiet ages fusing hydrogen to helium in their cores. When the simplest fuel runs down, the rhythm changes. In a star like our sun, gravity wins its arm wrestle for a moment. The core contracts and heats, while the outer layers swell. The star becomes a red giant, distended, cool at the surface, luminous. This is the time of shedding. Layer after layer loosens and drifts away in a steady wind, wrapping space in delicate shells. What's left in the middle is small and fierce, a white dwarf to be, not much larger than Earth, yet with a temperature that can exceed 100,000 degrees. Its ultraviolet light strikes the cast-off shells and makes them glow. For a brief span, tens of thousands of years, the star is surrounded by a luminous veil. We call it a planetary nebula, a historic misnomer born in the 1700s when small telescopes turned these soft disks into planet-like apparitions. They are not planets, and never were. They are the final breath of a quiet star. The physics is tidy. The red giant's outer atmosphere becomes loosely bound. A wind carries it away. The core's radiation ionizes the expanding gas, just as a bright lamp reveals fog. Hydrogen writes in red. Oxygen hums green-blue. Nitrogen leans orange. Through a spectrograph, those colors become code. Astronomers read composition, temperature, even motion from the pattern. Beauty and measurement arrive together. The Ring Nebula, M57 in Lyra, is a favorite portrait of such endings. Even a modest telescope shows a luminous oval hung in a field of stars, with a faint halo beyond. The ring is a shell, seen almost face-on. Inside, gas expands at about 20 kilometers per second, thin and orderly, driven outward, while the central remnant blazes. The symmetry speaks of a quiet departure, steady winds, stable geometry. Not every ending holds its shape so simply. The Dumbbell Nebula, M27, in Vulpecula, throws its light in two broad lobes joined by a narrow waist, a soft hourglass in space. The form hints at guidance, magnetic fields, and perhaps a companion star, focusing the outflow into opposite directions. Oxygen gives the nebula its vivid aqua. Hydrogen and nitrogen add red and orange. The blend looks like watercolor, a pastel of dissolution and grace. The whole structure continues to swell while the core cools. In a few thousand years, the glow will thin. The gas will merge with the interstellar medium. What was a star's skin will become the raw material of other stars. Closest to home, the Helix Nebula in Aquarius, about 700 light-years away, has earned a nickname, the Eye of God. Through optics, it looks like an iris wound in shades of blue-green, surrounded by a delicate halo. The shape is layered, shells a puffed spiral, viewed along its axis with a tiny white dwarf centered in the gaze. The helix hides a finer wonder, thousands of cometary knots, small, dense clumps of gas and dust shaped by the central radiation. Each knot trails a faint tail pointing away from the core, like a spray of miniature comets paused mid-flight. They are only systems sized on their own scale about the breadth of our solar system and number in the tens of thousands, giving the nebula a fibrous texture as if woven from smoke. Fragile and short-lived, they dissolve as the nebula expands, a lacework that unravels while you watch in slow motion. These scenes are not merely pretty prefaces to the dark, they are deliveries. The elements released carbon, oxygen, nitrogen seed the galaxy. Dust forms in the cooling flow, coating grains with ices and molecules that will one day help cool clouds and knit chemistry deeper than any single star could make alone. What looks like an ending is a distribution, a returning of ingredients to the pantry. 5 billion years from now, our sun will take its turn. It will swell to a red giant, likely swallow Mercury and Venus, and warm the orbit of Earth with a heat we could not withstand. Then it will shed, for a short, exquisite time, an expanding shell around the dying star, will glow in soft reds and greens, hydrogen, oxygen, before fading as the core cools. It is a melancholy picture, and yet comforting. The sun's last gift will not be ash but dust and gas that drift into the larger story and help write other mornings. Between the hush of birth and the hush of farewell, a star's life is mostly steady. Hydrogen burns to helium. In more massive stars, helium burns to carbon and oxygen, and so on. The details branch with mass, but the hum stays gentle. Fuse inward, shine outward, keep balance. The beginnings and endings are where contrast sharpens jets, sketching the dark at one end, rings and hourglasses at the other. In both cases, light reveals a process that is, at heart, simple. Gravity gathering, pressure answering, radiation carrying news to the wider world. Planetary nebulae wear many faces. Some drift as near-perfect rings, soft ovals that look like lanterns held up in a calm night. Others stretch into hourglasses, butterflies, or delicate shells, nested inside shells, as if a star's last breaths arrived in quiet pulses rather than a single sigh. The mechanism is the same each time. A tired star loosens its outer layers. The small, bright core left behind lights those layers from within, and for a brief season, the sky displays a glowing memory. The symmetry, you notice the circles, the paired lobes, the patterned halos, often reflects hidden helpers, a companion star leaning close, a magnetic field combing the flow, or a wind that changed character as the star aged. However varied the shapes, the feeling is steady, a final kindness of light before darkness has its turn. The colors in those images are more than a painter's choice. They are the voices of elements speaking at specific wavelengths, the emission lines of a thin gas responding to ultraviolet light. Astronomers use narrowband filters to isolate these notes. Hydrogen alpha for red, O3 for blue-green, S2 for a warm orange. Layered together, they become the dreamlike palettes that make planetary nebulae seem unreal and entirely true at once. What looks like art is chemistry with perfect manners, atoms relaxing after being shaken and telling you exactly who they are. These brief apparitions matter far beyond their beauty. Each glowing shell enriches the interstellar medium with heavier elements. Without that slow recycling, the galaxy would lean toward simplicity, mostly hydrogen and helium, not much story beyond them. Carbon for living cells, oxygen for water and air, nitrogen for the quiet work inside every leaf and lung. These pass outward in the final winds of ordinary stars and drift until gravity gathers them again. The night is full of farewells that become beginnings elsewhere. There's comfort in that. A star that is done with its long task still leaves a gift behind, a colored veil that persists for thousands of years, and long after the veil has thinned, its light is still on the way, crossing the dark with the news of what happened. When we look at the ring, the dumbbell, the helix, we are seeing echoes, transformations, already complete. One day, far ahead, someone may look toward the sun's remnant and see a faint glowing ring and give it a name, the way we named the others. The universe remembers with color. Some endings are more sculptor than lantern. Instead of a single rounded shell, the star's parting becomes geometry set in motion. Two long lobes mirrored across a thin, dark waist, like a butterfly lifting away from a flower. These bipolar nebulae combine delicacy with drama, symmetry with speed. At first glance, they seem too precise to be natural. The wings tapered, the waist sharply drawn. But the precision is simply physics, keeping good posture. The Butterfly Nebula, NGC 6302, is a famous exemplar. Twin wings, a few light years wide, shot through with orange, teal, and gold. The center hides one of the hottest known white dwarfs, with a surface temperature that climbs above 200,000 degrees. That core is a kind of steady blowtorch. Its ultraviolet floods the surrounding gas. Its wind plows and shapes, and a mirrored pattern grows from the balance. The term bipolar just means two lobes, two outflows along a shared axis. Why two? Because the outflow isn't free to go anywhere it chooses. Rotation can heap extra material along the star's equator, building a dense waste that blocks an easy escape on that plane. The path of least resistance runs along the poles, so the gas shoots outward there, forming opposing cones that stretch into hollow wings. Magnetic fields can further narrow or collimate those flows, combing ionized gas into tidy beams. And if a companion star is very near, its gravity can guide and tighten the outflow, or even stir fresh episodes of ejection, one pair of wings after another, each with a slightly different tilt. In the Butterfly, the gas in the lobes is racing outward at hundreds of kilometers per second. Closer to the waist, dust lanes absorb and scatter the center's harsh light, laying dark bars across the glow the way shadows fall through stained glass. It looks peaceful in photographs because time is stretched. What you are really seeing is a storm politely slowed, ripples where fast wind meets earlier, slower wind, shocks that brighten edges into clean lines, a pattern still changing, but too gradually for a single lifetime to notice. The Twin Jet Nebula, M2-9, carries the idea to an almost theatrical precision. Two lobes extend in perfect opposition, tips adorned with small knots of excited gas. The heart is a binary two stars circling each other. As the dying partner sheds its atmosphere, the companion's gravity draws a spiral through the flow and channels material toward the poles, where it is launched. The result is uncanny symmetry, so exact it can seem engineered, but there's no design in the human sense. There's only gravity and momentum keeping time together, with a little magnetism helping the lines stay true. Look closely, and the perfection frays in telling ways. One lobe might be slightly longer, one side a little brighter. Tiny asymmetries betray a companion's mass or a wobble in the flow. Color carries history too. Thur paints the lobes in cool aqua. Hydrogen and sulfur line the waist in warmer reds and oranges. Infrared images add another layer, dust lattices crossing the light, faint shock fronts rippling outward like rings on water. In some nebulae, you can even order these ripples in time, reading a chronology of dying breaths. A stronger wind here, a quieter interval there, a late pulse where the star changed its mind and gave more. All of it is temporary, 20,000 years or so, barely a sigh on galactic scales, and the wings lose their edge. The white dwarf cools. The pattern dissolves into the general medium. For the space of that sigh, though, a strict, soothing balance holds. If you could drift through one, the view would be austere and generous. A bright seed at the center, paired arcs curving away in mirrored grace, filaments drawn fine as silk, and then unraveling at the edges. This symmetry doesn't promise meaning. It offers ease. Even collapse can find order, when the pieces know where to go. There are endings that refuse symmetry entirely and choose radiance instead, catastrophes that light the day. In the summer of 1054, watchers in China and across the Islamic world noted a guest star, bright enough to cast a shadow and visible in daylight for weeks. They were witnessing the death of a massive star, a supernova that briefly rivaled the moon. When the flare faded, a faint cloud remained where the star had been. Centuries later, Charles Messier cataloged that cloud as M1, the first entry in the list he kept to avoid confusing such fuzzy things with comets. We call it the Crab Nebula. Through a telescope, the crab looks like a tangle, a web of fine filaments expanding into a softly glowing sea. It is chaos made legible. The original explosion released more energy in seconds than the sun will send out in all its life. And yet, 1,000 years later, the remnant reads as a lace of color suspended in calm. The tendrils are still stretching about 1,500 kilometers per second, and you can measure their motion by comparing old photographs with new ones. It is one of the rare places where the sky's change can be seen on human timescales. Wisps moved, knots shifted, space itself updated. At the center, the collapsed core endures a neutron star just 20 kilometers wide. The Crab pulsar spins about 30 times each second, its beams sweeping like a lighthouse across radio, optical, and X-ray wavelengths. Every pulse is a turn, every turn a reminder that energy didn't vanish. When the star died, it was rearranged. The pulsar's wind, a stream of high-energy particles, floods the nebula and keeps it bright. Where that wind presses against the inner gas, a luminous torus forms in X-rays, a compact ring that marks the engine's presence. Watch closely over years, and you can see ripples propagate outward from the center crests of brightness, marching through the haze like waves on a pond. Much of the crab's radiance is not from hot gas, but from something subtler, synchrotron light, emitted when charged particles spiral along magnetic fields at near light speed. That process produces a broad glow across the spectrum, a soft veil that overlays the sharper filaments. It's the hum beneath the melody, the reason the nebula looks as if it were lit from within by quiet electricity. The filaments themselves are the star's former skin, stretched and thinned by the blast strands of hydrogen and helium, braided with oxygen, nitrogen, sulfur, and heavier elements. Each thread is a record: how fast it was thrown, how it met the shock, how it cooled and recombined. Red from hydrogen, green from oxygen, blue from sulfur colors as evidence, not ornament. That evidence points beyond aesthetics. Supernova remnants like the crab are the great recyclers. They cast out the periodic table's middle and upper rows, carbon for living chemistry, calcium for bone, iron for blood and stone, silicon for rock so that later clouds will have richer raw material. The atoms in the hand you'd lift to point at the crab once sat in stars that burned and ended. Their ashes drifted until gravity gathered them here. The galaxy grows more articulate with each such event. The crab's structure reveals the choreography. Its roughly 10 light-year span contains an inner, smooth, energized plasma suffused by the pulsar wind, wrapped in an outer, delicate cage of filaments. The filaments move at different speeds. Some race ahead, others lag, tracing the blast's uneven push through the star's layered body. Magnetic fields bind and guide, kinking here, loosening there. In radio, the nebula is large and diffuse, the synchrotron sea, In optical light, the filaments pop into focus, veins and threads. In X-rays, the center tightens. The pulsar and its torus blaze. Jets protrude. The engine shows its gears. Each band contributes a truth. Together, they make a complete sentence. It is easy to forget how violent the first moment was. The star's iron core collapsed, gravity compressing matter until protons and electrons merged into neutrons, creating a sphere of nuclear density that could fit beneath a small city and outweigh mountains. The rebounding shock tore the star apart, and neutrinos, ghost particles from deep within, carried away more energy than anything else. For a heartbeat of cosmic time, the event outshone the galaxy. Then the light softened, the memory lengthened. The remnant learned how to glow with patience. This is the part that soothes. Catastrophe turned into order, noise into pattern. The crab hums with a rhythm now, the pulsars spin measured in flashes, the wisp's drift measured in years, the shell's expansion measured in centuries. It is controlled chaos, a sculpture of energy that keeps its shape even as every part of it moves. You can stand under a winter sky, think of a day recorded almost 1,000 years ago, and feel that the universe keeps a good ledger. Between a planetary nebula's ring and a supernova's lace is a wide country, but they belong to the same map. One is a soft farewell from a star that worked quietly. The other is a brilliant last shout from a star that lived hot and fast. Both return material to the common pool. Both lace space with structure that will matter later. Both are brief compared to the lifetimes of the stars they reveal. Both linger compared to the hours we can give them at a telescope eyepiece. And there is a thread that ties all of this back to us. The narrow-band greens and reds of a planetary nebula, the aqua sweep of a butterfly's wings, the multi-wavelength glow of a supernova's ghost. These are not just spectacles, they are reports. Hydrogen's line says, "Here is where ultraviolet touched me." Oxygen's line says, "Here, it was hot enough, rare enough for me to sing." Sulfur's line says, "A shock passed this way." The pulsar's ticking says, "The core came back as rhythm." Listening changes how the night feels. It becomes less a ceiling and more a conversation. The rhythm inside that tangle is gentle and sure. The pulsar ticks with a steady patience. The filaments drift outward like breath on a winter window. The hot gas cools by degrees, trading brightness for calm. Each layer moves in its own time, and together they make a kind of slow music notes, too long for a human day, harmonies written in centuries. The crab looks delicate, but delicacy here is only a way power chooses to appear. It holds the memory of a blast that startled eyes in 1054 and the power of 1,000 suns stretched into a lace of light. The glow that reaches you tonight began its journey nearly 7,000 years ago, when the star's outward streaking shell was already on its way. Long after the lighthouse at its center dims and the clockwork beam grows quiet, the elements flung outward will keep traveling, folding into new clouds, worlds, and mornings. The crab does not stand for ruin. It stands for continuation, flash to glow, pulse to hush, a metronome tapping time while the galaxy rearranges its ingredients for another verse. When a massive star dies in a brilliant shock, the flare is quick, a few heartbeats of catastrophic power, and then the aftermath begins its long work. A wave moves outward through space, cooling as it expands, sketching a sphere that soon becomes a web as it meets the grain of the interstellar medium. Where the wave strikes gas, it lights it. Where the gas is thin, the wave runs. Where it is thick, the wave slows and curls. The result, seen with patient instruments, is embroidery threads of red, aqua, and gold hung against night. Two places show this art with uncommon grace: the Veil Nebula in Cygnus and the Vela supernova remnant farther south. The Veil lies about 2,400 light-years away, the ghost of a star that burst 5 to 10 millennia ago. It isn't a single sheet, so much as many, most of them seen edge-on, so thin in places that they look like strands of silk. The bright edges are shock fronts, places where the expanding blast wave slams into gas, compresses it, heats it to extremes, strips electrons from atoms, and then, as the gas cools, lets those atoms glow while they recombine. Hydrogen whispering in red, oxygen shining in blue, sulfur humming in a greenish gold. Photographs catch the fine texture, the eastern veil like a pale flame rippling across dark. The western veil, nicknamed the witch's broom for its sweeping curve, Pickering's triangle, a lattice of angled filaments. You can forget how enormous it all is. The whole complex spans more than 100 light-years because the features are so slim, sometimes only a fraction of a light-year wide, smoke frozen mid-curl. The physics is straightforward and lovely. Look straight into a shock, and you see a soft haze. Look along the shock side, and the line sharpens into thread. Different colors map different temperatures and elements. The result is less like a painting and more like a legend. The spectrum is caption, each hue a label for a process that beauty moves. Compare images taken decades apart, and the filaments have crept outward. The whole thing balloons a little, breath drawn in slow motion. Eventually, the lace will fade as the gas cools and mixes back into its surroundings, pattern relaxing into fabric. For now, we find it mid-stitch, energy and elegance, sharing the same frame. Closer to the horizon of the southern sky, Vela offers a broader, more tangled version of the same story. Only about 800 light-years away and roughly 11,000 years old, the remnant sprawls across a patch of sky so wide it dwarfs the moon 8 times over, too faint and spread out to grasp in one glance without long exposures. Telescopes reveal arcs layered over arcs, filaments crossing in a depth that looks three-dimensional, shock fronts sliding through a clumpy medium, loops the size of small constellations, wisps fading into invisibility at the edges. In some places, the tangle overlaps with other ancient remnants, like the vast Gum Nebula, so that the scene becomes a palimpsest of blasts written over one another. The engine here is quieter than in the Crab, but just as steady. The Vela pulsar, a neutron star turning 11 times each second, sending its pulses in radio and gamma rays. It is a hum rather than a shout, a heartbeat that keeps the inner gas energized while shock fronts keep tracing the outer skin. Because Vela is close, its details are crisp, bright knots where density spiked, ripples marking where the shock met a cloud and wrapped around it, delicate folds that look as if thin fabric had been lifted by a breeze. In radio, you can see shells and filaments still moving outward at hundreds of kilometers per second. In optical light, the sutures catch the eye. In X-rays, hotter, interior structures glow like embers beneath ash. If you could condense time, you would watch a great bubble breathe, expanding, wrinkling, smoothing, and expanding again as it trades energy with its surroundings. Both remnants are classrooms for how energy travels. Shock waves compress gas, Magnetic fields steer charged particles. Heavy elements mix outward, seeding the medium with new chemistry. And beyond the lesson, there is the gentle reminder that the cycle is intact. The atoms, now singing in those threads, will someday settle into another cloud, help it cool, help it fall, and brighten again in the birth cries of future stars. The veil is a whisper, Vela is a sigh. Both tell the same truth. Even violence can end in grace. Across a different reach of sky, outside the Milky Way entirely, a region wakes and never quite sleeps. In the large Magellanic Cloud, a small galaxy that floats about 160,000 light-years from home, the Tarantula Nebula sprawls bright, busy, and tireless. Through a telescope, it earns its name. Long filaments radiate from a dense core, like legs from a body, and early observers, eager to translate shape into something familiar, saw a spider woven from light. The likeness is affectionate. Where a spider throws silk, this nebula throws energy. The pattern you see is feedback at colossal scale. Radiation, winds, and shock waves from massive stars carving cavities and walls, then triggering new stars in the compressed edges, and so on in repeating waves. At the heart sits R136, a cluster gathering some of the most massive and luminous stars known. Many tip above 100 solar masses. Together, they shine millions of times brighter than our Sunday. Their ultraviolet strips electrons from hydrogen across a region hundreds of light-years wide, turning it into a sea of glowing plasma. Their winds, streams of charged particles launched at thousands of kilometers per second, ram the surrounding gas, piling it into ridges and shells. The cavities they hollow are like bubbles pressed together until their walls knit into honeycomb. Along those glowing seams, gravity finds leverage and new stars begin. The efficiency is astonishing. Within a few hundred light-years, thousands of stars are being born, some cluster so tightly that the light blends into a single glare. That density makes the tarantula a rare window into how galaxies build stars in bursts. Inside the Milky Way, dust often blocks our wide view. The tarantula sits above the plane of a larger galaxy and angles into our sight cleanly, letting us watch the tug-of-war directly. Gravity gathering, radiation pushing back, magnetic fields threading the flow. The ridges and scalloped walls you see are the signatures of that tension. Each cavity, each arc, says there was a wind here, a wave there, a collision that warmed a seam until it shone. The process repeats at every scale. Small bubbles merge into larger ones. Their joined walls become long corridors where gas is dense. Along those corridors, small clusters bloom. The tarantula behaves like a miniature starburst, what entire galaxies do when their gas collapses into an episode of intense formation. In those times, a galaxy inhales, clouds fall and ignite. Then it exhales. Radiation and winds sweep clean, heating the medium and throttling new collapse. Later, when the gas cools, the rhythm begins again. The tarantula shows that breathing in close up, look with different eyes, and other layers appear. Radio maps pick up cold gas feeding the machine. Infrared shows the warm cocoons of deeply embedded stars still wrapped in their first blankets of dust. Ultraviolet outlines the newest, hottest clusters and the cavities they have scoured. X-rays trace shock-heated regions where winds collided head-on and raised temperatures to millions of degrees. The region is loud in wavelengths we cannot feel, a quiet roar of activity that, to the eye, smooths into serenity. Nothing here is static. The combined outflows from R136 push material far beyond the bright core, flushing the surrounding galaxy with heavier elements and stirring the interstellar medium. The feedback loops do what they always do: sculpt, enrich, regulate. Gravity is not the only writer. Radiation is an editor with a strong hand. On long time scales, the tarantula changes the Large Magellanic Cloud, just as earlier regions changed the Milky Way etching structure into a disk, feeding future clouds with better chemistry. There's time folded into the light. What you see tonight left the region 160,000 years ago, when humans were scratching color onto cave walls and telling the first stories around fires. That light carries a story of its own, a moment in the life of another galaxy, captured during a busy breath. It is also a mirror held at arm's length. By watching the tarantula, astronomers learn how Orion and Carina once looked in their liveliest days, and how similar regions still behave behind the veils of dust that hide them from us. The same choreography, gravity's pull, radiation's push, magnetism's guidance, plays across both stages, here and there, small and large. In the center, R136 testifies to what unchecked gravity can organize in very little time. Less than 2 million years old, the cluster is already reshaping a region more than 1,000 light-years across. Ultraviolet from its members floods the sea of hydrogen. Winds tear at the nearest walls. Shocks ring and ring again. Within that field, smaller groups take shape like eddies in a river. Some of the most massive stars are already shedding mass, destined for theatrical endings, supernovae that will press fresh waves into the surrounding gas, maybe even collapses that skip the fire and go directly to black holes. Each ending seeds the medium. Each wave starts another stanza. What the tarantula offers, beyond spectacle, is a lesson in scale. The same truths that cradle a single protostar inside a dusty ball, pressure versus pull, cooling versus heating, structure born of flow, reappear here across hundreds of light years. A galaxy breathes the way a cloud breathes, only slower, only larger. Energy cycles in and out of form, matter cycles in and out of bonds. Light carries news of both. The region is busy and yet soothing to watch because the tempo is beyond hurry. The most fevered processes, stretched across the distances involved, look like composure. Stand with that for a moment. A pulsar ticks and makes lace glow. A shock front writes calligraphy in Cygnus, while a southern bubble exhales. A spider of light hums in a neighboring galaxy, sickle bright along its ridges, soft along its corridors, its heart bright with impossible stars. None of these scenes argue. They collaborate. A star's death leaves threads that feed a star's birth. Threads coalesce into clouds. Clouds flower into clusters. Clusters carve bubbles. Bubbles compress walls. Walls gather clouds again. The rhythm is slow and kind. Even an explosion ends in pattern. Even a storm learns how to move with grace. If the Milky Way were a city seen from far above, the tarantula would be a district lit all night. The Vale, a neighborhood redecorating after a bright event. Vela, a broad park where 1,000-year breeze moves the long grass. And the Crab, a clock in the square. It's secondhand visible if you watch with enough patience. You are free to walk among them with your eyes, letting your breath find their tempo. Light left long ago to be on time for this. The universe has work to do, gathering, shaping, dissolving, And it does it without rush, pausing often to lay a thread of color across the dark so we can follow what is happening and feel, in the quiet between beats, that everything still belongs. We're looking homeward, too. The same processes that light a distant satellite galaxy once shaped the Milky Way, and they'll shape it again. A nebula's tangled web of gas and young suns is a reminder that the universe is not a still photograph, but a living network, forever renewing itself. The tarantula throws its bright threads across another galaxy, yet those threads reach here in spirit, woven into the same fabric that became our clouds, our stars, our stones, and us. Peering deeper into a nebula, you find that space isn't empty. It's quietly busy with chemistry. In the dark between stars, where visible light fades, cold molecular clouds host a patient workshop. Atoms bump and cling. Dust grains gather frost. Simple molecules form carbon monoxide, water, and then branch toward longer chains that hint at future complexity. It isn't chaos in a beaker. It's slow craft guided by temperature, time, and chance. The cosmos practices the art of becoming interesting. Our first reliable map to these hidden rooms came from a very ordinary molecule, carbon monoxide, CO. In visible light, molecular clouds are dark. In radio, CO glows softly. Hydrogen, the most abundant ingredient, is hard to see directly at such low temperatures because H2 keeps quiet. Co, with its gentle rotational spins, radiates at millimeter wavelengths that radio telescopes catch with ease. Trace CO, and you trace hydrogen by proxy, outlining the cold reservoirs where future stars will gather. The portrait that emerges is understated and beautiful. Vast, slow rivers of molecular gas drifting along spiral arms, interiors chilled to a few tens of degrees above absolute zero. Collisions are rare, but each one matters. Hydrogen pairs with oxygen to make H2O. Carbon meets oxygen to make CO and CO2. On the surfaces of dust, grains tiny silicate, or carbon specks, new reactions begin. These grains are the countertops of an interstellar kitchen, each coated in thin ices of water, carbon dioxide, ammonia, and methanol. When ultraviolet photons or passing cosmic rays nip at those ices, they break bonds. Fragments recombine. More complex molecules appear. Over millions of quiet years, this photochemistry cooks up organics, alcohols, simple sugars, long carbon chains. They aren't life, but they're its early grammar. Meteorites that fall to Earth still carry some of these relic molecules, fossils from chemistry that predated the sunday. In infrared light, many of these molecules reveal themselves through distinct fingerprints, subtle patterns of emission and absorption. Among the most widespread clues are PAHs, polycyclic aromatic hydrocarbons, flat carbon rings that resemble candle soot at a molecular scale. They form where carbon-rich gas cools inside the envelopes of waning stars in the general interstellar medium, even in galaxy outflows. Ultraviolet light tickles them. They fluoresce at mid-infrared wavelengths, producing bands so reliable that astronomers use them as star formation tracers. Where PAHs glow, young stars are often near, their UV whispering to the surrounding gas. The echo is comforting. Similar carbon ring structures underpin much of Earth's biology. To find their kin drifting between stars is to sense that nature reuses recipes whenever it can. Because this chemistry hides in cold dust, ordinary optical telescopes see almost nothing. Infrared and radio slip between grains and bring news. That's why instruments like Spitzer, ALMA, and the James Webb Space Telescope feel like the chemist's toolkit for space. They don't hunt for pretty shapes. They listen for vibrations, the stretch and bend of bonds at definite frequencies. Read those notes, and you can identify molecules one by one, even in darkness. Spitzer mapped mid-infrared PAH bands that traced our galaxy's arms like dim neon. ALMA, the Atacama Large Millimeter, Submillimeter Array, pushed further, catching complex organics in young star disks, methanol, formaldehyde, even ethyl alcohol where planets begin. James Webb sharpens the view again, resolving icy mantles and faint emissions in filigree detail. What once looked like a black void becomes a whispering world, full of signals waiting to be translated. The chemistry is slow, but relentless. Simple molecules beget intricate ones. Dust grains catalyze reactions the thin gas would never manage on its own. When a new star turns on, heat evaporates the local ices, releasing accumulated molecules back into space. Some destroyed, some rebuilt, many mixed into more clouds later. Bit by bit, the galaxy becomes more chemically articulate. Hydrogen, helium, and a pinch of carbon are enough to start. Repetition writes the rest. Molecules that store energy, carry charge, absorb light, and eventually, on warm worlds, join biology's circles. In places like Orion, the infrared glow of PAHs and other molecules lies like embers beneath the visible fire of hydrogen light. Dark clouds in Taurus and Ophiuchus, nearly invisible to the eye, blossom in infrared quiet nurseries, rich with promise. It's striking how little of this matches our everyday laboratory intuition. On Earth, we heat, stir, and confine. In space, the containers are dust grains, the catalysts are cosmic rays, and the heat arrives one photon at a time. Given enough patience, nature still finds a road to complexity. Molecular clouds are more than star factories. They're archives, preserving the record of every element forged in earlier generations of suns. Study them, and you're reading the preface to planets, and perhaps to life. Every nebula has its season. For a while, it glows ionized gas like soft lantern light, newborn stars heating the edges, dust tinting everything in rose and blue. Inevitably, the same stars that woke it begin to unmake it, pushing gas and dust away. What remains isn't emptiness, it's a new arrangement, a cluster of stars set free, drifting slowly from the nursery that built them. This transformation from cloud to cluster is the natural close of star formation. A collapsing cloud rarely turns itself wholly into stars. Only a fraction of the gas ever makes that leap. Even in the busiest nurseries, the star formation efficiency sits low, about 10%. The rest takes a different path, warmed by starlight, stirred by winds, eventually folded back into the galaxy. The universe, it seems, is more patient than productive. Massive hot stars begin to reshape their cradle almost as soon as they ignite. Their radiation ionizes hydrogen into a glowing plasma. Their winds carve cavities, piling gas into arcs and pillars. Over a few million years, the feedback adds up. Dozens of young heavyweights with short lives and loud voices raise the internal pressure until the nebula swells like a balloon. When pressure beats gravity, the cloud can't hold together. Gas leaks through openings and pours away. Gas blowout sounds dramatic. In reality, it's a long exhale. Over hundreds of thousands of years, the glow dims as material drifts outward. The baby stars, now unmasked, shine directly into space. The cloud thins to a faint wisp, and then to nothing you could outline. The nebula as an object dissolves. The cluster remains. Clusters come in many characters. Some are compact and tight-knit families like the Pleiades or the Hyades. Others are loose associations destined to drift apart within a few 100 million years. Their fates depend on shared mass and binding. Inside, stars span from tiny red dwarfs to brilliant blue giants, their numbers obeying a quiet rule: the stellar initial mass function. Think of it as a census that keeps turning out nearly the same across the galaxy. For each massive star, there are dozens of sun-like ones and hundreds of small red dwarfs. The pattern feels universal, the cosmos favoring balance. A few bright, short-lived architects to enrich the medium, many small, enduring lights to keep galactic night softly glowing for eons. The giants do the hauling. They live fast and loud and spread oxygen, carbon, iron, silicon, the heavy ingredients for later clouds, worlds, weather, and breath. The small stars supply stability. They burn with prudence for tens to hundreds of billions of years, a quiet background hum that outlasts drama. Together they run the galaxy's long economy, bright investments that pay in metals, steady accounts that keep the lights on. Young clusters linger tight at first, still feeling their common gravity. From afar, they resemble a swarm of fireflies, just released from a jar, dense, lively, proud of their escape. Time and motion ask no one's permission. As the cluster orbits the galactic center, tides stretch it. Encounters with passing stars or clouds disturb it. Members drift away. After a few 100 million years, the original pattern is faint, then lost. The stars continue alone, scattered like seeds on wind. That dispersal is not an ending. It's a turn of the wheel. The gas expelled during blowout doesn't vanish. It rejoins the interstellar medium diffuse, stirred and ready. Supernova shocks, stellar winds, and broad galactic tides need it. Here it compresses, there it thins. New clouds form cooler, denser, and the cycle begins again. In this sense, a galaxy is a recycling plant with perfect recall. Nothing is wasted, everything is transformed. Each loop leaves the medium slightly richer in metals and dust. Early stars were nearly pure hydrogen and helium. Each generation afterward adds to the palette. Today's clouds hold debris from uncounted ancestors. The atoms in your bones took that long way round, born in stellar cores, scattered in veils, condensed into rock and river and blood. When the light fades and the cloud dissolves, its beauty migrates. It lives on in the stars that were once hidden, in the trace metals coloring their light, in the molecules drifting between them. Orion's bright arcs, Carina's carved folds, the rosette's faint tendrils, each is a chapter in the same narrative, matter crossing the seam between darkness and glow, over and over, for billions of years. Galaxies don't evolve in sudden lurches, so much as in steady breaths. Cloud, cluster, dispersal, repeat. Some regions flare, others rest. The Milky Way inhales gas to form stars, exhales energy to spread it again. and keeps that rhythm without hurry. To watch a nebula fade is to witness that breath running backward. Brightness softens, colors pale, gas retreats into night. What looks like loss is transformation. The same atoms that blushed red in hydrogen light may blaze in a future star or shimmer in a distant planet's sky. Matter keeps moving. It only changes address. Even the stars we know by name carry echoes of this drift. Many bright points, Sirius, Vega, Altair, were likely born in clusters that have long since loosened and vanished. Their siblings are strewn across the disk, invisible to the naked eye but detectable by their shared motions and chemistry. Families can be traced not by proximity but by fingerprints, the ratios of elements in their atmospheres, the arcs of their orbits. It's a comforting thought that the sky's strangers are often relatives, far-flung, but related by a cloud they once shared. The stars remember, even when the nebula forgets, and the circle closes without hurry. Gas becomes stars. Stars reshape the gas. Remnants drift and gather again. The galaxy keeps breathing, never still, always renewing. Every glowing cloud is a brief blossom in a much longer cycle, a spark between two slow inhales. When the light softens and slips away, the quiet that follows isn't emptiness, it's potential, the same darkness that once gave birth to light, waiting with patient gravity for the next bright weaving. Nebulae aren't ornaments, they are the universe at work. Here, light and matter meet. Energy learns color. Endings lean into beginnings. Each hue is a clue to the hidden physics. Hydrogen writing in red, oxygen singing in blue-green, sulfur sketching soft orange along an edge where change walks in. Each shape carries a sentence, a pillar carved by starlight, a ring left by a farewell, a filament thinned by time. From far away, it can look like disorder. Up close, it becomes a calm conversation between creation and decay. Across these clouds, from Orion's bright folds to the veil's ghostly lace, the same patient rhythm repeats. Gas surrenders to gravity and falls inward. Stars ignite and etch their signatures on the walls that made them. Later, their ashes seed the dark with new ingredients. It isn't destruction, it's renewal, steady, sure, and endlessly resourceful. This is how the galaxy tidies itself, sweeping up old light, folding it into new forms, keeping the great breath moving. There's comfort in that thought. On the largest scales, nothing is wasted. What fades returns. What burns away will glow again, reshaped and reborn. The universe polishes its dust, rearranges its stars, and starts over, not once, but always. So let the last of tonight's light drift. Picture those soft clouds floating in a vast hush, color sliding through mist, newborn stars brightening and dimming like slow heartbeats. The night is patient. The cosmos is kind. Somewhere, even now, another nebula is learning to breathe. Close your eyes and follow that breath out, past the familiar constellations, past the quiet engines of distant clouds, until thought loosens and you rest inside the same gentle rhythm that turns darkness into dawn.